Okay, hello everybody. This is going to be our third video of the EMR topic. We're going to do this one asynchronously for a couple of reasons. One, we should have now covered two lessons. One, which was an introduction to EMR and on reflection. And now's kind of a good time to do a kind of an individual self-paced lesson. That way that if you have some questions, hopefully you'll have some class time right now to be able to ask me to maybe clear things up a little bit. Another reason why, though, is that there's some pretty tricky math we're going to do towards the end of this topic that's on refraction and lenses, and it kind of has a lot of optometry overlap. And I think this one really works well if you get a chance to kind of go at your own pace. There's really a lot of similarities between refraction and reflection in terms of the fact that we're going to be doing a lot of image diagrams. And so I should have shown you how to do some image lens diagrams where you draw ray diagrams. That's really the word I want to use, ray diagrams. Those are the ones where, if I were just to make a quick new page here, if you were to have like a surface like this, say this is a concave mirror, and you had a principal axis like this, and say you put a focal point right about here and maybe a center right about here. If you had an object over here, you hopefully are familiar a little bit with me doing something like this. You might put a line like this. So I guess I'll have to do it with just lines like this, where you draw a line that goes then through the focal point like this. And then if you had a line that went through the focal point like this, it would come out parallel. Hopefully this is a bit familiar. And you would then recognize that if anyone were to look in the mirror, they would see an upside down and smaller image. And the rationale behind that is that if this is an eyeball right here, if someone were to be looking in this direction right here, if they were to aim their eyesight at this point on the mirror right here, they would then be able to see this object over here. But if a different person were to look at the exact same object in the mirror, they wouldn't look at the same spot. If this person right here were to look at that same spot right there, they wouldn't see the right thing. But if they were to look at this spot over here, then yes, indeed, they could actually see the same thing. And so that's kind of what you hopefully have some ideas on. We're going to build on that concept today, and we do have some practice, obviously, we're going to do on that. But reflection and refraction are very similar. That being said, what I want to point out, though, is that they illustrate different ideas of the particle model or wave model of light. There's a few different concepts that we're going to discuss, one of which is going to be reflection. And reflection really helps to illustrate the idea that light, or EMR, seems to act as a particle. But today we're going to add on refraction. Eventually we're going to add on interference. We're also going to add on diffraction. And these three things right here, interference, diffraction, and refraction, they all seem to be evidence that light is acting as a bit of a wave. And then what we're going to eventually get into is talk about how the photoelectric effect just blew things apart and then resuggested that light and that electromagnetic radiation, they suggested that it actually acts like a particle again. And I mean, we're going to discuss a lot of history around this time in the course, but scientists were getting kind of confused because they had evidence that light was a particle, they had evidence that light was a wave, and eventually we'll get to talking about the double slit experiment for electrons, de Broglie's hypotheses, and basically discover that the answer is both. Light behaves as both a particle and a wave through duality and quantum physics, and it gets weird, and honestly, I can't even describe it to you right now. We just haven't learned enough. So why don't we just focus today on refraction? And again, I guess this is kind of why I got off on this tangent. We're doing this asynchronously, just because I think this is a good topic to kind of have you the ability to kind of pause to go back on. And probably most importantly, after having done a couple of lessons, this should give us a little time for you to have more one-on-one conversations with me. And I really want to encourage you to do that. If you've got questions where you're like, Chris, this isn't making sense, this is why I like doing a lesson asynchronously, so that we have some time for you to be able to have some like small group or one-on-one discussion type stuff. Because you don't necessarily ask as many questions when you do group lessons. So, okay, let's begin. Refraction. You guys should all be familiar with the concept of refraction. As I notice this, I actually see that reflection is written up here under the wave category. Maybe I'm going to change that just in case someone sees this. These two fit wave, and reflection is more like what a particle would do. Sorry, I'm a little scattered here, but okay, so let's talk refraction. Refraction being a property that we recognize that waves do, which is how they have the ability to change direction as they go from one medium to another. And you're probably familiar with seeing refraction. I've got a few slides that'll illustrate it. This first one right here is probably one of the best ones, where we know that this straw right here, we know that it's not like breaking up and bending sideways. I mean, you can actually see it bend right about here. You can see it bend right there. And then you actually see it literally move like right here and right there. There's kind of a gap there. And in this example right here, you can actually see how light is both going through air, glass, and water. In this section right here, light is bouncing off of the straw, and then as it bounces off of the straw, it basically goes in all directions, right? And what happens is the red light gets absorbed, and then the remaining light basically bounces off in 360 degrees, and some of that light then travels towards your eye, or in this example, the camera that took the picture, right? But in this middle section right here, the same thing happens. Light is going to be bouncing off of the straw, but before it comes to you or I to see, if it bounces out this way, that's one thing. But if it bounces straight out of the page towards our eyes, it has to travel through glass at some point. And as light travels through glass, it actually bends a little bit. And the same thing happens in the third section here. Light that travels through water will also bend differently. And so it makes the straw look bent. But we know the straw is not actually bent. It just has to do with the principle of refraction. And let's go to this slide right here. You probably have seen examples like this before. Maybe the best one is actually this slide right here. The one of like a person here that, say, wants to spearfish. What ends up happening is this person right here, their mind, their brain right here, seems to perceive, there's a brain, seems to perceive that the fish is in this top location, because your brain believes that things are traveling in straight lines. And so what really happened is waves bounced off of this fish in all directions. And so a light wave bounced this direction right here. But as it passed from the water to air medium, the wave actually bent and started traveling along a different trajectory. Now this person's brain right here interprets that signal and thinks, well, no, I think it was actually straight in front of me. And so really an optical illusion takes place where the person believes that the fish is right here, but it's actually lower. And fishermen and people who needed to basically try to catch fish in this sort of capacity, after a while they realized that they were always missing. If you tried to jam your spear basically right here, you'd always miss the fish. Once you understood, actually, no, the fish is actually a little bit below. If you aim your spear a little bit lower, you might actually hit this fish. And so this picture right here kind of illustrates the same thing. If you put a pencil in water, you can actually probably see the bending that's taking place. Like this photo right here, I think does a good job of it, letting you see the bending that takes place when you have different mediums. Okay. Now we're going to discuss some theory behind this later, but hopefully you're familiar with this concept of refraction. I got one more picture here, and then I'm going to talk about another practical application. But I mean, here's the exact same thing, right? Light rays are bouncing off the fish and into someone's eye. And I think it's really important that we recognize that, because often when we draw images like, say, this one right here, these ray diagrams, if I'm going to put an eyeball right here, an eyeball right here, if this is an eye or if this is an eye, we kind of like to consider that the eye is traveling along this trajectory. But that's not really true, right? Light is bouncing off of this object towards the mirror or lens, and then bouncing towards our eye. But we kind of think of like what would happen if our eyes shot laser beams, if you could shoot laser beams out of your eye and have it reverse its trajectory. Sometimes we like to think of it that way too. So hopefully what I'm saying here makes sense. If not, maybe pause the video and ask me to clarify. Before I move on, I want to point out that there is one really big application of needing to bend light. And maybe you know where I'm going already. It's optometry. Optometrists, basically, that's their entire livelihood, right? It's being able to bend light into people's eyes so that it refracts and they can see better. Glasses or contact lenses or corrective surgery. They can now do things where they can actually implant a lens into your eye so that you don't even need to wear glasses or contacts anymore. It's a permanent lens inside your eye to make it so that you can, you can refract light properly so that your brain interprets it the way you need to. That's kind of based on how like your eyes shape basically will slowly change over time, causing your vision to deteriorate. So when we do this lesson here, really think about optometry. That's a main focal point. So okay, so let's move on here. Back in the year 1600, Willebrord Snell, I think it's actually his full name was Snellius. I believe he was Finnish or something like that. Anyways, he discovered the law of refraction. He at least was the guy who finally put it together. Because scientists have known about refraction for thousands of years. I mean, similar to reflection, people have figured out, oh, there's optical illusions that can take place. And so Snell finally figured out how to put them together. And he realized that there was a direct relationship between a couple of variables. There's a direct relationship between the amount of angle that something bends, as well as the wavelength that it has, as well as the velocity that it's traveling. And I'll get to that in a little bit here, but he realized there was a direct relationship. But there's also an indirect relationship between those variables and what he called n. And n is basically what he called the index of refraction. And maybe the best way of me describing it is, I have it down here actually. I was going to write the word up here, density. But I've got it down here, the optical density of the material. For any of you who have glasses, and I do, I have a prescription that's like one of those like -0.6, -0.7. I have fairly thick glasses when I'm wearing them. And the reason why is that I need a fairly dense lens material in my glasses to bend light more. The more that you have of the optical density, the more index of refraction you basically have. And so there were certain things that have a high index of refraction. For example, diamond has an N value of 2.42. And basically that means diamonds bend light a lot, which is why they actually look so shiny, because we see light refract out of diamonds and bend a lot. Water is also fairly dense. Air, by the way, air has a value usually of 1.0003. And the reason why it's not 1 right on the dot is that we consider a vacuum complete nothingness to have an N value of 1. That's basically the benchmark. A value of 1 repeating, like basically 1.0 repeating, would be a vacuum. We would consider that to have absolutely no reason for light to bend because there's literally nothing in it to refract, right? There's no material, there's no medium in a vacuum for refraction to take place. Air, because we have an atmosphere on Earth, it has a pretty minimal amount of refraction. So we usually consider air to be 1.00, and this is actually on your data sheet. The N value for air is 1.00, which basically means it's our benchmark. If something is traveling through air, it has no refraction. But if you now send light through diamond or water or something else, plastic, then it changes its index of refraction. So here's a chart that kind of shows a few different things here. It mentions what I just had there. The vacuum and air are here, but the little star next to this one for air just lets you know that when we do this in experiments, we're allowed to use the value 1.00 as our value. It's on your data sheet. So let's try an example here. And I'm going to try to illustrate how I like to solve these problems here. I always try to draw a boundary, and this boundary really describes the fact that there's two different medium. Hopefully you know what I mean by the word medium. It's the stuff that things are traveling through, right? Maybe we've even already discussed the idea that mechanical waves require a medium, right? Often mechanical waves travel through water. Like when you see water go up and down, that requires a medium. But we know that electromagnetic waves don't even require a medium. They can travel through a vacuum. They don't even need physical matter to travel through. But here we're talking about a boundary between two different types of physical matter. So that's your medium. So what I'm going to do is I'm going to have a beam of light traveling in glycerin. So on one side right here, I'm going to write out glycerin. And I'm going to have that wave travel through glycerin. Now, I'm going to undo this in a second, but let's say that reflection happened. We would then know that the wave would bounce right back, and there would be an angle such that the two angles on either side are basically equal to each other. But that's not what's going to happen in this case. We're actually going to have this bend. That being said, the concept of a normal still matters. And so if reflection happens, yeah, this thing would bounce back that way. But refraction is going to take place. And it's going to refract from glycerin into water, it looks like. So I always like to try to write out boundary, water, glycerin. I want to write out what's going on. And it says that we're going to go from glycerin into water. Okay? And what's going to end up happening here is this is going to bend. And so as a way of trying to describe this, I'm basically going to draw it bending like this now, where it's now going to change its trajectory, just like back in one of these pictures here. It's going to change its trajectory somehow. It was going one way, now it's going to go another way. Okay, so I'm going to start with a picture that looks like this. And it mentions, in terms of numbers, that it hit the water at an angle of 45 degrees with the normal, 43 degrees with normal, so that's 43 right there. And what it would like to know is, what is the angle going to be right here? As it bends, how's that going to work? So let's try to solve this question using Snell's law. Basically, the way Snell's law works is it's a 4-part law. You can use any of these variables here. There's relationships between angles, there's relationships between wavelengths, velocities, as well as a flipped relationship between that and the index of refraction. So you just need to pick the stuff you know, and in our example right here, we know information about the indexes of refraction and the angles we have. So I'm just going to write that part out. So the way this law works is that sine of theta 1 over sine of theta 2 is equivalent to n2 over n1. So there's the part of the law we're going to use. And then the last thing I'm going to point out is that whenever I solve a question like this, I always like to try to make sure I label which side is which. So why don't I just make water be side 1 and glycerin be side 2? That was arbitrary that I chose it that way, but the reason why to me this is important is I want to make sure that I'm always consistent with what I make 1 and 2. So this is a pretty straightforward question now, actually. Let's plug in some numbers. I'm going to do sine of theta 1. And I don't actually know what theta 1 is because that's actually what we're being asked to solve for. I'm going to divide by sine of theta 2. And so theta 2 would be the glycerin angle, so that's 43 degrees. Then I need n2, which is glycerin's n value, which is right here, 1.47, a very thick medium. And then I'm going to divide that by n1, which is water's index of refraction, which is 1.33, which is still thick, but not as much as glycerin. And now I basically just need to solve for theta. So if you're stuck on how to do the algebra, can you call me over and I'll try to help a little bit here. But I'm going to do what I probably shouldn't do. You should never assume, but I'm going to assume that you can handle the algebra here and solve for theta. And I got a value with what looks like 2 sig digs to be 49 degrees. So pause the video and try that. And if you don't get an angle of 49 degrees, can you call me over? I'll try to help you explain something. But this actually is the first physics principle that I need to point out. And I want to go back to this picture right here. If I were to draw a normal line right about here, you would notice that the angle that it was leaving, the angle that the light was leaving the water at, compared to the angle that it now bends when you're in air, the angle got bigger. There was a smaller angle with the normal here. And we always measure to the normal, by the way. So there's a smaller angle here. And then as it went into air, it opened up more. The angle got larger. And there is a principle that I need you to know, which I'm sure I have written on a future slide, but I'm just going to say it right now. The principle is that if you're ever going from a dense medium into a less dense medium, it bends away from the normal. And so this picture that I've drawn here, I've actually drawn incorrectly, but I did that on purpose. I knew in advance that I was going to make this point. Because what should happen is that it should actually bend more like this. Apparently I'm using a thicker pen all of a sudden now. Whatever, this will work. I guess I'll draw with thicker pen the whole time now. So there we go. This was our trajectory, and it's actually going to bend this way because the angle has now opened up to 49 degrees. It was 43 degrees to start with. That's 43. Just fix that. Apparently I used a thicker pen all of a sudden. I don't know how I did that. Well, we'll go with it. 40, oh, that's not where it goes. It always goes with the normal. So here's 43 degrees. The normal is our up and down line there, right? So anyways, hopefully that makes sense. The theory I need you to know then is if you're ever going from a thick medium to a less thick medium, it bends away from the normal. And the opposite happens in the other direction. If you ever go into a thicker medium, things bend towards the normal. Yeah, perfect. That's my next slide here. That's what I was hoping for. So this basically describes what I'm saying. Say you have a ray that's going from, say, from air. That's maybe what this picture is saying. From air into water. So it's actually now traveling from a medium with like an n value of, say, 1.00 into a medium with an n value of 1.33. What ends up happening is it's always going to bend towards the normal line. It's always bending this way. And this may lead to a question that you're saying, Chris, why does it do that? Well, we actually have a rationale for that. We believe we know why. It has to do with some quantum mechanics, which we haven't even discussed yet. But basically, what light tends to do is it wants to find the path of least resistance. You probably heard that phrase before. Path of least resistance. And what it's looking to do is because it's traveling in water, one of the things that we've also learned, we didn't do in this example here, but velocity is one of the things that gets impacted. And so there is an inverse relationship between the, like a reciprocal relationship between the medium that you're traveling in and the velocity that you're going to have. See how the ends are flipped? Which means if you go into a higher medium, this velocity right here ends up going down more. And so that means your second medium is going to have a lower velocity, which means it slows down. And so therefore, by the path of least resistance, when you're in a thicker medium, you actually have to travel slower, and therefore you want the fastest way out. Imagine that this ray right here kept trying to go along this trajectory right here in order to get out of the water. See how much distance it would have to travel? But if it bends closer to the normal, rather than having to travel from here to try to get out of the thick, dense water in which it has to travel slower, it's now going to go from here to here instead. And it actually, because it has to travel slower, it chooses through some sort of quantum process, we'll get to that one day, but it chooses a shorter pathway in order to do so. So, I mean, maybe the analogy I would give for path of least resistance is imagine this is a person. Imagine a person all of a sudden has to cross a field of mud, and they need to get over to here. This is where they need to get to. Or at least they need to get to the other side. Let's just go with that, right? If they keep traveling on the trajectory they're going on, they need to slog through this mud, and therefore they're going to travel slower. But if they bend their path towards the normal a bit more, then what ends up happening is then they get out of this mud faster, but it's because they were traveling a slower speed. So what we've actually discovered is that light will actually travel slower speeds when it's inside different mediums. We know that the speed of light is actually supposed to be 3.00 times 10 to the 8, but it will actually slow down if you're traveling in diamond or if you're traveling in glycerin. Light will actually slow down as it bends. Now some kids would ask, well, Chris, why doesn't it just bend right to here? Wouldn't the shortest way across be straight across? And that's very true. And this is where light is still a bit of a mystery, perplexing. I mean, we know that it bends somewhat towards a new axis, but it doesn't find literally the shortest path. I imagine the rationale for that is that this n value is only 1.33. And so if its n value became 1.7, well, it needs to be able to bend to there. And if it becomes 1.9, it needs to be able to bend to there. And if we could ever have an infinitely dense medium, then it would actually bend completely parallel. So we need to leave some latitude for the idea of perhaps infinity. So there is some quantum rules to this, where like apparently what we think is somewhat like a quantum computer is able to calculate all permutations simultaneously. Light is able to do that as well, and it then picks the optimum path. And if you know what I'm talking about in terms of quantum level stuff, maybe that explains it. And maybe I just spoke right over your heads, because we haven't even gotten to quantum stuff yet. But yeah, if you know what a quantum computer does, where it calculates all algorithms simultaneously rather than one after another, scientists believe that light kind of behaves along a similar pathway, and it somehow manages to find the path of least resistance. So anyways, I'm going to move on because I've got lots more to cover here. So pause, rewind, ask me more questions. Let's try another one here. Let's say there's a beam of light with a wavelength of 700 nanometers. That's what NN stands for, nanometers. And it's going to travel from air into glass. So I'm going to do it like this. Here's going to be side 1. This is going to be air. I'm going to label this side 1. This is going to be side 2. It's going to be glass. And it's going to be going from air into glass. And I just want to point out that I already know how this is going to bend. If it's going from air into glass, I know that air is less dense than glass. And so therefore, its trajectory will change like this. It's going to try to find a shorter way out, right? If you can kind of imagine that this is a glass prism, like a piece of glass right here. Light is coming into the glass, and it is going to bend, try to find a shorter way out. And so this is angle 1 right here, and this is angle 2 right here. And I guarantee you angle 2 is going to be a little bit shorter, right? But I also know my relationships as well. And so I know that as you increase the index of refraction, what ends up happening is the angle will decrease. But I also know that the wavelength will decrease, and I also know that the velocity will decrease. There is a reciprocal relationship between increasing an index of refraction. The angle has to now get smaller, but so does the wavelength and so does the velocity. And so this thing is going to travel slower. So it's going to actually ask me what's the new wavelength of the color in the glass, which is kind of cool because while it's in the glass, this color is actually going to change. The wavelength is actually going to change in terms of how that looks. So Anyways, let's try our example here. I just need to extend the page. What I'm looking to do now is that same formula, but I only care about certain parts of it. I care about the N2 over N1 portion, and I care about the wavelength 1 over wavelength 2 portion. So if I kind of go back up to meet maybe halfway here, let's plug in some values. N2 is going to be the medium for glass, which based on the previous slide, glass is, maybe it says it in the blurb above. There it is, glass, 1.75. So glass is going to be number 2. This value is going to get 1.75. And 1 will be the value for air, and so air is 1.00. Then we need the wavelength in air, which was 700 nanometers. And I know the units aren't in meters, but it's fine because they're basically, as long as you start in nanometers, you'll finish in nanometers. And so what I'm really doing is solving for wavelength 2, so this is the one I'm unsure of. So I can probably just take it right from here. If you're a little stuck on how to solve with fractions, call me over. I can give you help with the algebra part, but hopefully you can do this. Wavelength 2 is going to be equal to 700 times by 1.00, divide by 1.75. Hopefully I didn't lose you on that step right there. If I did, call me over. But essentially I times this up over there, that one there, and that one there. I did the old switcheroo. So, and what should happen is, remember that inverse relationship I just mentioned? Well, 700 is now being divided by 1.75, and I now get 400 nanometers. And so, like I said, there is a relationship between the wavelength and the index of refraction, is that as you have a bigger index of refraction, you are getting a smaller wavelength. And you're also getting a smaller velocity, you're also getting a smaller angle because it tries to find that path of least resistance and bend towards the normal. So this is crazy, but if you were able to somehow be a person inside of the light right there, 700 nanometers is red, by the way. If you were to be physically inside the glass, you would see it as purple, because purple is basically where 400 nanometers exists. Now here's the crazy thing though, we're outside of the glass still though. So we'd have to actually literally be inside the glass with that frame of reference, because what's actually going to happen is as the light then reemerges from this prism, it would actually bend right back again the same way that it was going, and it would come right back to being red again. The math that we just did would undo itself, and what this angle came in at, it would actually come right back out at again there. And I'm going to do some demos later in class to kind of illustrate that. But yeah, hopefully that made sense. I'm going to move on to another example here. Because the next thing we need to talk about is some applications of how refracting light is useful. And there are 3 main ones. We're going to talk about internal reflection, then we're going to talk about prisms, and then finally we're going to talk about optics and glasses and how we can make lenses out of this. So the first example I've got here is that we can actually bend light so much that it actually doesn't bend anymore. It reflects. I mean, this is really the principle of reflection. Imagine that you try to take some light that was in water, for example, and you try to let it come out of water. And what ends up happening is we know that it's going to then bend away from the normal. This angle right here is going to increase. And here's that principle again. If you have a n value that is increasing, nope, sorry, not increasing, decreasing, because it was an n value of 133, and now it's an n value of 1. So we've dropped our n value. What ends up happening is our angle goes up, as well as our velocity going up, as well as our wavelength, not frequency, our wavelength is also going to increase. And so yeah, that's what's going to happen here. But we can maybe increase our angle so much that eventually the angle isn't just, say, 50 degrees or 70 degrees. Eventually the angle becomes 90 degrees. Or, compared to the normal, maybe the angle now becomes 120 degrees. Well, as soon as the angle gets over 90 degrees and becomes 120 degrees, it wasn't refracted anymore, it was reflected. And the key word is we can actually trap light, or really any electromagnetic radiation. Light is just one form of it, right? Remember that whole spectrum where it goes like this and eventually gets smaller, where one side is radio waves, the other side over here is gamma rays, and light is somewhere in the middle. Visible light is in the middle. So this can happen for any type of signal or radiation, but yeah, you can actually trap light in its medium. And one of the best examples we have of this is something called a fiber optic cable. What fiber optic cables do is they have such a dense medium that a signal can't even get out of them. And it basically bounces around inside of the cable infinitely. I'm going to do a new slide to kind of illustrate this. Imagine that this is a fiber optic cable, and it is so dense that a signal tries to go this way, and it bends so much that it would have gone on this trajectory, but it bends. And it doesn't just bend to here, it doesn't even just bend to here. It bends back and bends back on itself and bounces this way. And then it wants to escape on this side, but again, the medium for your fiber optic cable is so thick that it can't escape this way. It can't even escape this way, it actually bends back. And what ends up happening is a signal bounces back and forth through your fiber optic cable without a loss of signal, which is really cool. And yeah, it can travel basically infinitely as it bounces around inside due to total internal reflection. So here's kind of another picture that illustrates this. The word we use is it's known as the critical angle. The critical angle is the angle that you need to have so that the beam can't leave the object, and so that at least it skims along the surface of the water. Like right here, see this angle right here? This angle right here is allowing it to have a larger angle here, right? The angle is increasing. This might have been, say, 10 degrees, but now it's increased to 20 degrees. But let's say that I started at 45 degrees. Well, now 45 degrees is increased to 90 degrees. Well, let's say that I open it up to 60 degrees. Now my angle of reflection has now become 120 degrees. So what I'm trying to say is that if you increase your angle more and more and more as this thing comes, if you increase your incoming angle, you'll also increase your outgoing angle. This is your first angle, and this is your second angle. And so there's also a direct relationship between those, where if you increase one of these, you increase the other. Now, it's not actually a direct relationship between the angle. It's actually a direct relationship between the sine. And so if I were to plot a graph of sine of theta 1 and sine of theta 2, there's a direct relationship there. Or if you increase the first angle, it will actually increase the second angle proportionally based on sine. And this is a number that you don't need to memorize, but basically 48.8 degrees is the angle required right here, so that if you income with a certain amount of angle, then light's can internally reflect. The key that you need to know about this is that the critical angle, and this is super important, so I'm hoping you're going to make note of this. Take notes, write this down. But the critical angle always means that the outcoming angle is 90 degrees. The outgoing angle has to be 90 degrees. And if it's at least 90 degrees, then that means your incoming critical angle won't let the angle escape. If it's anything less than 90 degrees, then actually refraction happens. But if your angle becomes more than 90 degrees, like 91, 92, 93, then you get reflection. So that's one of the applications you need to know about. Basically theory concepts. Here's another one, prisms. What ends up happening as light travels through a prism is that it bends, right? Now, if you're not aware of this, white light, like light that comes from the sun, we consider to be white light, it is really comprised of all of the colors of the rainbow, but they need to be separated, because they're coming in all parallel to each other. And so what ends up happening is if you send light through a prism, wavelengths of different lengths refract more, right? What we know is that there's a relationship between sine of theta as well as like the angle, which is comparable to your wavelengths. And so different wavelengths have different angle deviations, right? What ends up happening basically is that red light deviates less than purple light. That is the key principle here. You can actually see in this picture of the prism is that white light was wanting to go along this trajectory right here, but it started to bend, and it actually bends twice. These things have to be in like a triangle or something else, because let me show you why here. Let's say that you took light and you bent it into a rectangular prism. So then it would like say bend like this. But then it would actually bend right back to where it came, so that your first line and your second line were parallel to each other. And you wouldn't have any dispersion. But if you set up the geometry so that you get kind of a triangle out of it, what ends up happening is it bends once, and then it bends a second time, and it really spreads out the light. And I've got some pictures to kind of illustrate this, but this is a principle you need to know, though. I put it right here, key concept. You need to memorize that red light deviates less than purple light. Here's some pictures to describe it. Imagine that you had some blue light. Blue light would come in just like this, right? And it would want to go along this trajectory. But what ends up happening is blue light bends once right here, and it bends a second time right here. And so blue light bends a lot, right? Whereas red light doesn't bend quite as much. Red light came in like this. It wanted to go in a straight path, but it bends a little bit here and a little bit there. And if you kind of compare the two, that's why we get the rainbow effect. The rationale behind it is that there's a relationship that I have right here in Snell's law, where there's a relationship between the angle you have, technically it's the sine of the angle, but there's a relationship between the angle you have and the wavelength you have. Now, you might say, well, hang on a sec here. Wouldn't that mean that if you increase your wavelength, you then increase your angle? But the angle that you have is always with the normal. I need to point that out on this slide right here. I drew a normal line into this picture right here. The angle with the normal would be right here. There's the angle with the normal. And as we want to look at red, you'll actually see that red's angle actually bends smaller. Okay? The angle compared to the normal, ooh, I need a finer pen to be able to draw in here. Let's see whether I can make that pen become smaller again. How did I do that? I can use a calligraphy pen. Okay. So the angle that's in here, oh, that's not going to work. Hopefully you can still see that. So here's the original trajectory, right? It wasn't going to go this way. And it wants to go along its straight line, right? But the angle compared to the normal, which is this black line right here, right here, is the first angle. And I'll use another color to illustrate the second one. Here in red, there we go. That's a good way of describing it. There's that one there. And hopefully you can see that the angle got smaller, right? Don't we know that the angle is supposed to get smaller, right? As it goes into a thicker medium, it's supposed to bend towards the normal, right? And so the normal is right here, and it bent more towards the normal than it was originally traveling, right? Here. Where's the angle with the normal? The angle with the normal is actually right here. There we go. Maybe I can draw that a little better. So this was our original angle. Let's call this angle right here 50 degrees. Well, now red's angle now is going to only be 40 degrees. Can you see how the angle has dropped, hopefully? Let me try that one more time, because I can't draw small enough to illustrate this as well as I'd like to. Let's do this again. This is another reason why I want to do this lesson asynchronously, because hopefully you can see that. Here is your original angle with the normal, right there. Let's call that 50 degrees. Well, red light, when you put something in a newer medium, red light is going to get a smaller angle. It is. It's going to get a smaller angle. It's now 40 degrees only, right? And that makes sense, hopefully, right? As it bends towards the normal, and you get a smaller angle, right? And so the light was supposed to go along this trajectory right here, but the light bent towards the normal instead. And so the normal is over here, and so the light bent this way. And that's towards your normal, because the black line was your normal line. But now what I want to try to illustrate is that based on wavelengths of, say, orange, well, orange actually bent a little bit more. And so orange actually bent so that it has an angle with a normal of 30 degrees. It bent more from where it was supposed to go, but it has a smaller angle. I got to say that again. It was supposed to go this way, and so therefore orange bent more. But because of that, it has a smaller angle. And that's where this relationship comes in, is that if you increase your wavelength, you're going to drop your angle. Remember your wavelengths? Your wavelengths are like this picture right here. So your wavelengths, basically what's going to happen, well, actually, no, this is a direct relationship. I need to actually illustrate this better. Yeah, here we go. There's a direct relationship between your wavelength and your angle. I don't know why I had one up, one down earlier. But what we should say that is that if you increase your wavelength, you should be increasing your deviation, right? And so, well, you don't increase your deviation, you increase your angle. And your angle right here, if you guys can see, which of these colors right here has the greatest angle? It's red. Okay, purple right here has just a little bitty angle in there, right? And the reason why is that purple has the lowest wavelength. So the lowest wavelength would have the lowest angle. Yellow has a bigger angle. And so yellow has a higher wavelength, right? Remember on a curve like this, yellow, this is going to be red over here, and purple's going to be over here. So yellow actually has a higher wavelength. And so because yellow has a higher wavelength, it has a higher angle from the normal. Red would be over here, and red would have the highest from the normal. There's a direct relationship here. And so this would be red. Red is going to have the highest angle from the normal like this. But this is kind of backwards. This is what kids really struggle with, is that although the angle is lower for purple, it's the angle with the normal. And so therefore it underwent more deviation. Because if it underwent like say like this straight on right here would be no bending whatsoever. And so if you have an angle of say 5 degrees like purple has right here, 5 degrees from the normal means this thing bent a ton from where it was supposed to be. Does that make sense? Like 50 degrees, if you could have this thing come out at 50 degrees, if it goes in at 50 degrees and comes out at 50 degrees, it didn't change at all. But if it goes in at 50 degrees and comes out at 5 degrees, it bent a ton. So what ends up happening is a higher angle happens because of a higher wavelength. A lower angle happens because of a lower wavelength. There's a direct relationship there. And it's an inverse relationship between your n value. Maybe that's why I had, if the n value increases, what ends up happening is both your angle decreases, as well as your velocity decreases, as well as your wavelength decreases. So, wow, this is tough to try to explain in this picture here. Again, this is why we're doing this asynchronously, because if this doesn't make sense to you, call me over. Let me try to explain it to you one-on-one. So, okay, so there's the second thing that we know theory-wise. There's really no math to this. You just need to understand the theory. And so maybe just memorize this right here. Red light deviates less than purple light. If you can understand that, that's a great place to start, is that red will bend less. But it actually means it has a higher angle compared to the normal. It depends on what you're comparing it to. You're comparing it to the normal. So the normal would have been like right here. This would be the normal right here. Right? If I draw this in, this is your normal line. And so compared to the normal, purple has a very small angle, whereas red has a bigger angle. So therefore, the higher the wavelength, the higher the angle that it bends. Not the angle that it bends, the higher the angle that it is from the normal. Because keep in mind, straight would have been right here. Okay, hopefully that made sense. I got to move on. Okay, the third application we're going to talk about is lenses. And we're going to spend a decent amount of time on this and then do a couple of examples. Lenses are basically like optometry, right? Like your optometrist, your eye doctor focuses on this. And they're very similar to mirrors. We're actually going to redo some work on mirrors and lenses today. And if I taught you the reflection lesson and you didn't fully understand it and you're wondering, Chris, why are you moving on from reflection to refraction? One of the reasons is that we kind of cover the same sort of concepts with lenses, and so there's a lot of similarities there. One of the big differences, though, in lenses is, first of all, as a ray passes through a lens, it doesn't bounce off of it like that. It goes through it and it bends one way or another. It either bends inwards or it bends outwards. But like rays are supposed to go through lenses. So there's two different kinds. There are converging and diverging lenses. And for those of you who have different prescriptions, that's where you have like positive and negative prescription amounts, because it tells you basically whether we need light to converge or diverge in your eyes. If you're like me, I have a prescription. My eyes are bad. One of my prescriptions is like a negative 6.75. And so that the negative, we're actually going to talk about that in a little while, but it describes basically what kind of lens you need. So let's move on here. Lenses are often used for really a couple of different things. We're either going to project or magnify things. And it really depends on whether or not whether or not you're planning on trying to send light through a lens, like for example right here. In this example right here, imagine that this wasn't a person, but imagine that this was like a laser pointer of light. And I've got an image I'm going to use later. Well, maybe what you'd like to do is send an image through, like projectors. A projector or a screen is going to project light through. And what ends up happening is as it goes through the lens, all of those light rays are going to bend, and you can actually put like a screen over here. And you can actually project an image onto a screen. This is literally what happens in your eyes, actually. Your eyes recognize light rays coming in. And what ends up happening is they get projected onto the back of your eye, onto your retinas. And then your brain interprets that signal. And one of the cool things is that it actually causes sometimes these pictures to show up upside down. If you didn't know this, your eye interprets everything upside down, and your brain flips it back right side up for you. There was a really cool experiment in the 1800s, actually, where scientists tried to put on goggles on people that flipped the world upside down, and eventually people's eyes compensated. because what your brain does is it actually takes an upside down image, and in your brain it flips it the other way again. So anyways, this would be a good example of something that's being projected. You're shooting it through a lens, and in doing so, you can actually put a screen over here, just like the whiteboard projector has a screen, and you then see an image on the other side. This one over here would be for magnification, and the best way I can describe this is if you were to look with your eye over here through a lens like this, the actual object is right here, but what ends up happening is you see an object right here that's smaller. And this is what glasses do. Your eyes are right here, and you're seeing something through it, and we use it for magnification. What you're actually seeing is something smaller. We can also make it look bigger. That's also possible too if you'd like, depending on the lens. But this is how you focus something. So what I'd like to do right now actually is show you a little emulator. Hopefully this shows up well. But here's a little online tool that I found that kind of illustrates how this is going to work. What we have here is a lens. And I can play around with different things. I can make the lens have see how it's become like a thicker lens here, and now a thinner lens. And what ends up happening is as I move this object around, it changes where the light rays cause it to bend through. And so this would be a good example of a projector. Imagine that this right here is the lens that is in the overhead projector that I would often project on the screen. And over here, right here, this is the actual image on the screen you have. What overhead projectors do, or what just like regular projectors do, is they project an image. So like light gets shot out of here, and it's shot through a lens, and then over here is the whiteboard screen. And that's actually why projectors are often mounted upside down, although you can change this, but they're mounted upside down because of the fact that what ends up happening is it actually flips the image upside down. It used to be right side up, it needs to flip it upside down. And as you play around with different characteristics, you can make it either smaller, or like an overhead projector needs to do. If you can kind of imagine this, you need to make it larger. So if you put it ridiculously close right here, you can actually make it so, well, you can't see it anymore, obviously. I should move this back, I guess. But hopefully you get the idea. Here it's small, and as I move it closer and closer and closer, I can make this thing become magnified and blow up an image on the screen. Now, maybe one of the best ways of illustrating this is actually to make it so there's a screen here. This is kind of cool. If I were to take a lamp right here, if I were to make the lamp kind of move around a little bit, you can see that there's no image on the screen right now. And the reason why is we need to find where all of those rays converge. And so what I'm going to do is I'm going to set up the distance between the lens and the smartboard to go to right here, and watch what happens. As I move this thing further and further away, there's no image that shows up. But over here, if I now put the lens right here, now the image is showing up, and if I put it right there, it can now be in focus. If you've ever been to the optometrist, they'll often ask you, they ask you to pick is 1 or 2 clearer or blurrier, right? And what they're really doing is they're messing around with the distance, or they're messing around with the refractive curvature. And so this could be 1, and this could be 2. This could be 3, and this could be 4. You see how they're messing around with different variables? They're trying to find the optimum spot so that right there it comes into focus, right at that point right there where all of these rays converge. And if I were to go back again, not to the screen, but say to this image right here, this is now where all of a sudden the image is being projected. So hopefully that makes a little bit of sense. We're going to move on and do some of the math on this now. So I'm going to go back to my notes here. When you do drawings like this, you always have to have your principal axis and a principal plane. And what that means is that you have to draw your axis like this, and you have to draw an up-down vertical axis as well. And the reason why is that when you have a lens, unlike a mirror which only has 1/2 to it, you actually have 2 sides to it now. You always have 2 sides to these lenses right here. And because there's 2 sides, there's 2 focal points. Because what ends up happening is this side right here is a concave side with a focal point right there. But, let's use another color. This side right here also has a focal point right there. See how these 2 sides right here, they all have their own focal points? So basically, you don't do double the work, you just have to change how you approach this problem. Rays that pass through the focus always go parallel. That's the same rule we had last time. Rays that are parallel pass through the focus, and anything going through the center just goes straight on. Here's a bit of a picture here. Anything that was going parallel basically goes through the focal point. And anything that goes through this focal point goes parallel, and anything that goes right through the dead center of the lens keeps going straight. And what ends up happening is if I had an image over here that I projected through the lens, I could make it bigger and upside down on a screen, just like the projector in class does. I'd make it larger. So let's do a ray diagram for this lens. Let's try to figure out what's going on here. So the first thing we need to point out is that we actually have two focal points, and I want to draw them in here. One of the focal points right here is this guy here, and it's the purple one right here. What we have here is a concave side of a lens right here. And there's a second focal point over here based on this concave blue section right here. So there's where we're starting. We've got a double concave lens. This is going to be a diverging lens, and you'll see why in a bit here. Oh, this is where I seem to have changed the thickness. I need the line tool. Here we go. Let's try the first one. The first rule is that let's send a ray in parallel. Okay. Well, imagine that we now are dealing with the purple side of the lens right here. If this was a mirror, what would have happened, if this was a mirror, is this lens would have then bounced back to the focal point just like this. And what I'm going to do, though, is I'm going to continue this line as though it kind of continued like this. I'm going to draw some arrows here, so bear with me for a second. If this was a mirror, here's how this would have worked. We would have suggested that light rays would have bounced this way, this way, this way, this way, this way. And then they would have bounced back this way. That's what would have happened if this was a mirror. But it's not a mirror, this is a lens. And so light rays would have gone like this, and then they would have traveled through, because light rays are supposed to go through a lens like this. So therefore, these are actually going to diverge outwards. Okay. Let's try another ray diagram here. Let's send some light through this focal point right here. So let's say the light went through this focal point right here, the nearest one like this. Well, what would end up happening here is if it was a mirror, it would have bounced back this way. And maybe what I would do is I would kind of continue this line going like that. That's not bad. I'm just going to make it go a little bit lower. Like, ooh, didn't mean to change that one. I want this one. Come on. Just to line it up. Okay, and so if this was a mirror, let's talk about what a mirror would do. A mirror would mean a ray would go like this, like this, like this. It would hit there and it would bounce back like this. And if there was a mirror, we would have had an image showing up right here. And a person right here and a person right here would both have to aim their vision at this spot to see it. And because the image was on this side right here, we would call it a real image. That's what we would have called it if it was a mirror. The way mirrors work is that anything on the opposite side is virtual, and anything on the same side is real. That's how we define things for a mirror. However, for a lens, light is not supposed to bounce off of a lens. Light is supposed to go through a lens. And so light would have gone through like this, and it would have actually taken this trajectory. And we would call this, we would say that it diverged. Right? That's actually how we would describe this. Light was going to diverge like this. Okay. One of the other things that would happen here then is that, oh, I actually drew that one wrong. Oh, I made a mistake here. You know what? I drew it as though it was a mirror, but I actually need to show you something else. I got to keep going backwards. If this was a lens, however, we would actually aim this at the far focal point. You actually aim at the far focal point, and what ends up happening is as soon as it hits the surface, at that point, now it bends. So this was good because I could illustrate the difference between things. So I'm just going to delete one of these lines here. Boy, there's so many lines going on right now. Let's use another color, because sometimes there's too many colors going on. This is one of the hardest topics, by the way. I'm going to aim this at the far focal point. But what ends up happening is as soon as it hits the mirror right here, it basically travels like this. So now we'll talk about what makes this different for a lens. What happens for the lens is, where's the pencil tool? What would happen here? Here we go. Is the light would have gone like this, like this, like this, like this. Now, if it was a mirror, it would have bounced backwards. But what's going to happen is it's going to go this way now. So the light is going to travel through it like this. So what would have gone to the focal point actually bends parallel. Okay. And then we're going to do one more example right here. For the last example, I'm going to, where's my line tool? Let's use pink. Anything that goes right through the center basically continues going straight through the center. Nothing changes when you go through the center. So light that was bouncing like this basically would have gone straight through along the pink axis, and it wouldn't change at all. Basically, it doesn't refract in the slightest. Now, we call this a diverging lens. And I'm going to do hopefully some examples in class, if I haven't already, showing you how light is going to scatter here. But what's happened here is this light is now scattered in all different directions. And you might say, Chris, how in the world is this useful? Well, the reason why this was useful is, let's say that your eye is right here, or your eye is right here. I don't really care, but let's just say that light is showing up right here. What ends up happening is all of these eyes perceive the light as though it all emanated at one source. All of these lines converge basically right from here. And so if this person right here wants to see this object, they have to aim at this spot right here. And if this person right here wants to see this object, they have to aim at this spot right here. I'm going to put a big X on it. That's where all my lines converged. And if this person over here wants to see this object, you don't actually look right there. You actually have to look at this spot right here to see that object. And what ends up happening is, this would be like how glasses work. All of these people right here, they are seeing a smaller line. Boy, I'm so sorry, this is so messy right now. But what's happening is all of these people are seeing a smaller but more in focus object right here. All of these rays, you see them right here. The actual object is right here. Actual object is right here. But this is where the image shows up. And you actually see it smaller. Hopefully we're going to take some lenses, and you'll actually be able to see that if you take a double concave lens, you can actually see a smaller object there. Now, what ends up happening for terminology here is that light is supposed to go through. Oh, I didn't mean to change that. Oh, I just changed something here. Hopefully the screen still works. Light is supposed to go through a lens. And so what that means then is that, you know how when we were doing the mirror, on the mirror, this side over here was virtual, and this side over here was real? Well, convention gets flipped. On a lens, this side over here is virtual, this side here is real. And so what you're seeing now is a virtual image on this side over here. And if I could go show you with some manipulatives, hopefully I have those out today. If not, I'll grab them another day, I guess. But that's basically what happens, is you're now seeing a smaller image. Here's basically a picture that shows a couple of possibilities. This would be an example of, say, a person then looking at a project image on a screen, and what they're seeing right here, remember how I wrote this out a second ago? These people here are now seeing a real image over here, because light is supposed to go through here. And so on this side right here, you're supposed to be seeing on a screen an image. So a person standing here, or a person with an eyeball here, or a person with an eyeball here, they are all seeing a projected image on a whiteboard screen. And so that's shooting light through a lens. However, a lens like this, what ends up happening is, as you're looking through this lens right here, you're actually seeing a smaller version of the real object. So, okay, hopefully this makes sense. I need to move on. We're going to do some of the math examples. I've got some notes here for how this looks. What ends up happening is converging lenses always have positive focal lengths, and diverging lenses have negative focal lengths, which means that me, with my prescription of negative 6.75 for my glasses, means my glasses are diverging lenses. And if any of you have glasses, take a look through them. You probably have concave lenses slightly. And so what ends up happening is the rays, they diverge like I just showed in this diagram here. And so we give it a negative focal length. The other thing that we point out is that when we try to figure out real and virtual images, the numbers that we use are everything that's on the other side of the lens gets to be positive, and everything that's on the same side of the lens as your object is negative. And the rationale for that is that light is supposed to go through lenses. So unlike mirrors, in a mirror we flip it. In a mirror, this would have been negative, this would have been positive. But in a lens, we flip these values. We're going to do a lab, hopefully a little bit later in our unit, whatever day I have it scheduled on, where if you're thinking, holy smokes, Chris, there's a lot to remember here, we're going to do some hands-on stuff with this. So I believe I have one last example, and we're going to call this a day. So let's do a math example. These are the exact same formulas, by the way, that we used in the last example. These are always the optic formulas. It's 1 over F equals 1 over DI plus 1 over DO. It's the same math that we're still going to use. And I'm going to try to draw this first, and this will be our last example. We're going to have a converging lens. So a converging lens is this one like this. It's this guy here, which means there's a focal length here and there's a focal length here. Here's the two focal lengths. And converging lenses have positive focal lengths. Remember how I just wrote that there? Converging lenses have positive focal lengths. So when we use the focal length in the formula, it's got a value of 0.22. And what we're going to do is we're going to put an object 0.41 meters in front of the lens. So that means if right here, this is 0.22, if we put an object 0.41 meters in front of the lens, that's actually right about back here at 0.41. Let's talk about how this array diagram is going to work real quick. First, we're going to have something go like this. And what's going to happen is it's then going to bend towards the focal point over there. That's going to be our first one. Then the second one is that we're going to then send it through this focal point. And as we send it through this focal point, it actually is going to bend parallel. So the one that was parallel bends through the focal point. The one that goes through the focal point bends parallel. And if I've done this well, the final one is that the one that goes through the center, and boy, I didn't do it well, but anything that goes through the center should hopefully go through uninhibited. And I didn't draw this really to scale, but what I'd like to point out is that this would be a projection type of scenario, where what we're going to want to do is shoot some light through this lens, and it's going to show up on a screen over here upside down. Now, based on my picture, it looks like it's going to be smaller, but I'm not sure that I've drawn my picture to scale. So although my picture makes it look like it's smaller, this may actually be larger. And let's just do this diagram right here. What we basically have here is this scenario. We're going to project something through there, and maybe this will work, right? Right here's my focal point. And then I'm shooting some light through the focal point, and all of these rays converged here upside down. So hopefully that showed up and you can see it. Let's do the math now, okay? Because the math is pretty straightforward. You just need to not screw up positive and negative. We're going to make this 1 over positive 0.22, 1 over the distance to the image. Well, that's what we're looking for, because this right here will be my image. And what I now need to figure out is 1 over distance to my object. Well, the object was over here, but this side gets to be positive, this side gets to be negative. So I have to make this be negative 0.41, because my object is on the negative side. And by the way, in lens examples, the object is always on the negative side. So DO should pretty much always be on the negative side. I can't really think of an example as to why the object would not be on the opposite side, right? Because we always want rays to be going through our lens. So therefore, the object needs to be on the side where rays can go through a lens. So anyways, from here, we just need to solve for DI. So it's going to look something like this. 1 over 0.22. If I add 1 over 0.41, it'll equal 1 over DI. And if I then take the reciprocal of both sides, I'll solve for DI. So DI is going to be 1 over 0.22 plus 1 over 0.41. And if I reciprocal that, I get a DI value of 0.143. And what that would mean then is that I don't think I've really drawn this one to scale all that well. Let me just check this one more time. We're going to use a positive focal length of 0.22. Yeah, that went right there. We're going to use a negative object image of 0.41. I'm just checking my math. 0.22, 0.41. Yeah. And so my image, now the answer that I got is positive, and that makes sense as to why it's a positive, because if this thing is a positive value, it should have showed up on this side over here. And in terms of its characteristics, I would then say that this is now going to be a, how does it work again? This is going to be a real image. And it's real because we expect light to go through. And so since we expect light to go through, we consider it to be a real image. Based on this, it doesn't matter where any eyeballs are. If you're sitting in your desks here or here or here, if you guys are all in rows, and these are all your eyeballs here, and you're looking at the screen, this is the whiteboard screen, who cares where you are? You're all going to be able to see this image projected, which is basically what's happening here. What's going on here then is that based on this scale right here, that's probably a better way of doing it here, is that as I've got this one right here, here's my focal length, and here's my object. It looks like it's actually kind of closer and maybe smaller even. We could even use the magnification formula to solve for how tall it is. I won't do that right now, but you guys can do that. Remember, there's a magnification formula. It's like a negative dO over dI. Here, I'll go find it. I'll go back and we'll end with our lesson here because we're already at an hour and 5 minutes. But if you guys remember from the reflection section, here's, ooh, I went way too far back. Here's the formulas that we need. If we also know the dI and the dO, we can solve for the magnification. So negative dI over dO will give you your magnification. Here, I may as well try this real quick. The distance to the object, I believe we said, was negative 0.42, I think. And the distance to the image was going to be positive 0.143, something like that. So if I take negative 0.42, I hope I wrote that value down right. I'll check real quick. And I divide by this value here. Oops, made a mistake. Negative 0.42 divided by the answer I just got. I have a magnification of negative 2.93, basically. The negative makes sense because it's upside down, right? Ooh, didn't want that one. I wanted this one. See how the object is now going to be upside down? Yeah. Object's going to be upside down, and with it being upside down, it also looks like it's gotten larger as well, which hopefully that makes sense. Hopefully I didn't make any mistakes. So the distance to the image was 0.42. Let's go find that last slide and just confirm. I always hate when I make mistakes if I do the videos that I'm showing you. But this is a long video. I need to wrap things up because you're probably not even going to finish this in class anymore. Where was it? Oh, it's 0.41. I'm sorry. Okay, so change it to 0.41, but you'll get the same sort of thing. Okay, we need to wrap this up. If this doesn't fully make sense yet, good. It shouldn't. This takes a long time. People need to go to school for years to become optometrists. I don't expect you to understand optics in an hour and 10 minutes. Optometrists have to go to school for a 4-year bachelor degree, then probably 3 more years of becoming a doctor, probably more than that, really. So please take it easy on yourself if after this lesson you don't understand optics 100%. But we're going to do a lab pretty quick here, where hopefully we're going to try to give you some examples to kind of see how this works. And really what we need to make sure you understand then is how lenses, as well as how mirrors, have both concave and convex, and how you can make real and virtual images depending on where things go. So why don't we wrap this up for now and ask me some questions. The run time right now is like an hour and 10 minutes almost, so this should be a good time to stop. We'll chat later. Thanks, everybody.